Good afternoon, ladies and gentlemen. Welcome to lecture. What I would like to present to you today is bearing capacity of soils with respect to shallow foundations. The lowest part of a structure is usually named as foundation, as you see in the figure here. And its duty is to deliver the load of the structure to the soil where it is resting. Suitable design needs that the load transmitted should not overstress the soil, because overstressing of soil might bring about excessive settlement or shear failure of soil, which would impair the structure. Therefore, for geotechnical and structural engineers interested in foundation design, it is vital to evaluate the safe bearing capacity of soils. A foundation design has to satisfy two fundamental requirements. The first one is the foundation must not fall down. That is to say, the shear failure of soil supporting the foundation does not take place. This is called the ultimate limit state. The second one is settlement of foundation must be within tolerable limits so that the design function of the structure is not damaged. This is called serviceability limit. In this lecture, we will only take into consideration the soil bearing capacity of shallow foundations. They are generally embedded at shallow depths, such as a depth less than their width. Alternatively, they may be regarded as being constructed within the reach of normal excavation planned. That is to say, the excavation depth is less than about 3 meters. There is a variety of shallow foundations, but typical ones are illustrated below. The first one is isolated footing, which is also called single footing. And the second one is combined footing, and the third one is continuous footing. There are two design procedures adopted in practice. One is allowable stress design, which is ASD in short, and the other is load and resistance factor design, which is LRFD in short. In ASD design method, the ultimate load resistance is obtained, and then this is divided by a factor of safety to get the allowable load or stress. ASD is the conventional design method. LRFD is dependent on reliability methods regarding the uncertainties in loads, soil resistance, method of analysis, and construction. The loads are multiplied by load factors, usually greater than 1, in different combinations, and the ultimate soil resistance is multiplied by a factor called the performance factor, usually less than 1. The governing equation for design dependent on LRFD is given here, where gamma is load factor, Q is load, capital R sub n is resistance, and phi is the resistance factor. Gamma and phi are the same symbols as unit weight and the internal friction angle of soil, so do not mix them. Eta is a ductility, redundancy, and importance factor. And I is the load type, such as dead load or live load, and the resistance type. Courts, engineering organizations, and agencies may have their own advices on load and resistance factors and load combinations. Here, we will only consider two types of load, namely dead load and live load, and a limited set of performance factors. They are aimed only to show how to apply these methods. In ASD, the load combination is dead load plus live load. However, in LRFD, the load combination is 1.25 times dead load plus 1.75 times live load. 1.25 and 1.75 are the load factors, as stressed before, to take into account uncertainties. A set of resistance factors as presented in the following table here. In practice, however, you should adopt the suitable resistance factor based on your local practice. Failure is defined as mobilizing the full shear strength value of the soil escorted by large and excessive settlements. The mechanism leading to failure for shallow foundations depends on the soil type, especially its compressibility and the type of loading. The first type of failure mode is called general shear failure. Its characteristics are well-defined continuous slip surface up to ground level, as you see in the figure. Heaving occurs on both sides, as illustrated here, and failure is sudden and catastrophic. Ultimate value is peak value, as illustrated in the graph here. This type of failure mechanism occurs in low compressible soils, very dense sands, and saturated clays under undrained loading when the soil is subjected to fast loading. The second type of failure mode is called local shear failure. Its characteristics are well-defined slip surfaces just below the foundation, but these slip surfaces fail to extend to the ground level. Large vertical displacements needed before the slip surfaces appear at ground level. Some heaving takes place on both sides, as you see in the figure, with no tilting and no catastrophic failure of foundation, and no peak value and ultimate value not defined, as you see in the figure here. This type of failure takes place in moderate compressible soil and medium dense sands. The third type of failure mode is named as punching shear failure. Its characteristics are well-defined slip surfaces only below the foundation, as you see here, and they don't spread on both sides. Large vertical displacements produced by soil compressibility, no heaving, no tilting or catastrophic failure. And there is no ultimate value, as you see in the figure here. Compression will densify the soil. This type of failure takes place in high compressible soils, very loose sands, partially saturated clays, normally consolidated clay in drained condition when the soil is subjected to very slow loading, and peats, in other words, organic soils. An expression for bearing capacity is dependent on the failure mechanism for a rough strip footing embedded at a depth df measured from the ground surface, as you see in the figure, where the soil in zones 1, 2, and 3 is in a state of plastic equilibrium. The active Frangian zone is pushed downwards, and in turn this pushes the radial shear zones sideways and the passive Frangian zones both sideways and upwards. The rupture line JD, JE are arcs of logarithmic spiral, as you see here. And DF and EG, as shown in the figure, DF and EG are the straight lines. The lines AE, BD, EG, and DF make angles of 45 minus 5 over 2 as illustrated in the figure here. If the law per unit area is applied to the footing, as you see here in the free body diagram of soil wedge, and if general shear failure takes place, we may say that passive force is acting on each phases of the soil wedge A, B, J, as you see in the figure here. And in this case, passive force should be inclined at an angle phi to the perpendicular drawn to the wedge faces. Since AJ and BJ are inclined at an angle phi to the horizontal, the direction of passive forces should be vertical. Now, considering the free body diagram of soil wedge and a unit length of the footing, for equilibrium, equation 1 can be written, where W is the weight of soil wedge, and ABJ is equal to the definition given here, where C is cohesive force acting along AJ and BJ, equal to unit cohesion times the length of each phase, as expressed here. Therefore, equation 2 can simply be obtained. Substituting equation 2 into equation 1, we get equation 4 as presented here. Equation 4 can be written in the form given in equation 5. This equation is referred to as Terzaki's bearing capacity equation, in which NC and Q and gamma are bearing capacity factors. K gamma, Kc, and Kq are earth pressure coefficients, which are functions of the soil friction angle. Terzaki recommended that for local shear failure, internal friction angle and the cohesion should be reduced to 0.67 times their values, or as formulated here. Nevertheless, we will consider only the equations for general shear failure that has gained common use in geotechnical practices. After the development of Terzaki's bearing capacity equation, several researchers such as Meyerhoff, Hansen, Vesic worked in this area and clarified the solution. Different solutions show that the bearing capacity factors N, C, and NQ do not change much and recommended as follows. However, for a given value of phi, the values of N gamma obtained by the above-mentioned researchers vary widely. The difference is due to the variation of the assumption of the wedge shape of soil located directly beneath the footing. So, the more conservative expression given by Hansen is this. But for all practical purposes, keep in mind that Terzaki's bearing capacity factors will lead to good results. The soil bearing capacity equation for a strip footing produced by Terzaki is modified for general use by including the following factors. Since Terzaki equation was produced for a strip foundation where the shearing of soil was presumed in only 2 dimensions, however, for rectangular foundations, the shearing of soil will also happen at the ends, causing an enhanced end effect. On the other hand, for circular and square foundations, a 3-dimensional mass of soil will be sheared. These effects are taken into account in a semi-empirical manner by modifying the equation using the shape factors SC and SQ. The shape factor S gamma related to the subweight term provides a reduction of bearing capacity due to shape because of the reduced confinement of the soil provided by rectangular, square, or circular foundations. Shape factors from Hansen are adopted in here and given below. Depth factors contribute to the bearing capacity of soil which could be obtained from shearing to the soil above the foundation level. Expressions for depth factors taken from Hansen are presented here. And when D sub F greater than B, which means when the embedded depth of foundation is greater than its width, dF over B should be replaced by tangent to the power of -1 times dF over B. Inclination factors are also adopted from Hansen. When the internal friction angle is 0, we use the first expression. When the internal friction angle is greater than 0, we use the second expression. Other inclination factors are also presented here. Base inclination factors adopted from Hansen are also shown here. Bear in mind that theta to be used in these expressions should be in radians. And finally, ground inclination factors. They are taken from Hansen as well and given here. Now, including all these factors, in the general bearing capacity equation put forward by Terzaki, we get the modified general bearing capacity as shown here. The question is, it appears that there are several general equations for estimating soil bearing capacity currently in use put forward by Terzaki, Meyerhof, Hansen, and Vesic. Are there any difference between them? Or which one is preferable? Well, as a result of observations, the following can be considered in selecting one of them. Terzaki is best for very cohesive soils where d sub f over b is less than or equal to unity, or for a quick estimate of ultimate bearing capacity with reference to other methods. But don't use it for footings with moments and or horizontal forces, or for tilted bases and sloping ground. Hansen, Meyerhof, and Vesic are best for any situation that applies, depending on user's choice or familiarity with a particular method. Hansen and Vesic are best when base is tilted, when footing is on a slope, or when d sub f over b is greater than unity. Many foundations have to be designed for the effects of horizontal loading or moment loading delivered by the structure to the foundation, both of which could lead to overturning. In order to carry out the analysis, it is vital to resolve the loading into a single total vertical load acting at the foundation level, with the moment and horizontal load effects taken into consideration by placing the total load at an eccentricity E as shown in the figure. The location of vertical load may be eccentric along both the long and short axis as you see in the figure here, leading to eccentricities E sub L and E sub B respectively. A convenient and conservative approach assumes that vertical load acts centrally on an effective foundation area as you see in the figure, ignoring the area outside of this effective area. So the bearing capacity equation for central vertical loading can be employed. So the general bearing capacity expression is then rearranged accordingly as shown here. Are there other factors that may affect the bearing capacity of soil? Yes, different soil strength. The undrained condition in clay soil, which is the short-term condition, the bearing capacity of cohesive soils with low permeability is the most critical one immediately after construction, before the excess pore pressure has time to dissipate. This is undrained condition. In this case, the shear strength parameters represented by undrained cohesion intercept or undrained shear strength and undrained internal friction angle, which is equal to 0. This condition will lead to the bearing capacity expression as formulated here. For internal friction angle equal to 0, the lower bound value of N sub C is then taken as 5.14 to be on the safe side. The drained condition in clayey soil, which is long-term case. After construction, as the consolidation takes place in a saturated cohesive soil, the excess pore pressure will dissipate and the effective stress will increase, thus increasing the shear strength of soil. Shear strength parameters is then represented by C prime and phi prime, which is greater than 0. And the ultimate bearing capacity should be rearranged accordingly as shown here. Now, another condition is the drain condition in sand, short and long-term cases. The allowable bearing capacity of sand depends primarily on the relative density, stress history, the position of water with respect to foundation level, and the size of the footing. Of secondary importance are particle shape and size distribution. The shear strength parameters is then represented by C prime and phi prime. Phi prime is greater than 0. And the bearing capacity formula should be rearranged accordingly as presented here. Shape, depth, and inclination factors depends on the choice of cohesion intercept and internal friction values as well. Therefore, different factors will be obtained based on the soil strength case assumed. In the derivation of the bearing capacity equations in the previous section, it is presumed that the groundwater table is located at a great depth with respect to the width of the footing. Nevertheless, if the groundwater table is close to footing, the total unit weight should be replaced by the effective unit weight in calculations wherever applicable. Now, if the water table lies B meter, which is the width of the footing as you see in the figure, or more below the foundation base, then general bearing capacity equation does not need modification. If the water table is just beneath the base of footing as shown in the figure, then the bearing capacity equation should be modified accordingly, where gamma prime is the submerged unit weight of soil. If the water table lies within B meter below the foundation level, as illustrated in the figure here, then a value of gamma prime could be obtained by linear interpolation between total and effective unit weight depending on the actual depth of water table beneath foundation level. Since the water table is likely to fluctuate during the life of the structure, it would be reasonable to adopt gamma prime regardless of water table. If the water table is above the base of the footing as shown in the figure here, or at the ground surface, then the bearing capacity equation should be altered accordingly as illustrated here, where gamma prime is equal to, Q prime is equal to gamma prime times h sub w. H sub w is the height of water from the base of footing. No simple satisfactory analytical method is now available to determine the bearing capacity of layered soils. A geotechnical engineer can apply a set of practical guidelines or use numerical tools such as the finite element method for analyzing layered soils. The basic problem, however, lies in determining and defining the soil parameters for those soils. We will refer to some practical guidelines for three common cases: a soft layer over a stiff layer, or a stiff layer over a soft layer, clay, and thinly stratified soils. Now, let us consider soft clay layer or stiff clay layer. Usually, shallow foundations on soft clays should be avoided, except for lightly loaded structures such as one-story buildings. Removing the soft clay and replacing it with compacted fills should be taken into consideration. Nevertheless, the bearing capacity using the methods described earlier should be computed before making a decision to replace the soft clay layer. Stiff clay layer or soft clay layer. The bearing capacity for this case is the smaller value of treating the stiff clay as if the soft clay layer does not exist, and assuming that the footing punches through the stiff clay and is supported on the soft clay layer. The bearing capacity is the sum of the shear required to punch through a vertical plane in the stiff clay and the bearing capacity of soft clay layer. Only a fraction, about 2/3 to 1.5 of the undrained shear strength should be employed in the calculation of the shear resistance on the vertical plane in the stiff clay layer. Another method is to place an imaginary footing on the soft clay layer with dimensions B plus TSC times L plus TSC, where B and L are the width and length of the foundation, and TSC is the thickness of the stiff clay layer below the base of the footing, and then calculate the ultimate net bearing capacity using bearing capacity equations. Thinly stratified soils. Under these circumstances, dip foundations should be preferred. If dip foundations are not cost-effective, then the bearing capacity can be computed by using the shear strength parameters for the weakest layer. Alternatively, harmonic mean values for C and phi can be calculated, and then these values can be used to calculate the bearing capacity. Generally, a factor of safety is applied to the ultimate soil bearing capacity to obtain the value of allowable bearing capacity. There are two basic definitions of the allowable bearing capacity of shallow foundations. They are gross allowable bearing capacity and net allowable bearing capacity. Let us see what they are. Q ultimate is usually regarded as the gross ultimate bearing capacity. Therefore, the net ultimate bearing capacity is the difference between the gross ultimate bearing capacity minus the weight of excavated soil. Gamma as the unit weight of foundation soil, and d sub f as the depth of foundation as illustrated in the figure here. This is used to obtain the net allowable bearing capacity, which is a ratio between Q ultimate net bearing capacity and the factor of safety. On the other hand, the gross allowable bearing capacity can be computed as Q ultimate divided by factor of safety plus the weight of excavated soil. The question is, how can we select a value of factor of safety to make sure that the risk of failure of the foundation as well as the structure is avoidable or at least minimized? For these, a combination of both structural and geotechnical factors has to be considered. These may include the following: the ambiguity of loading, specifically with non-routine buildings and live loading effects which are difficult to predict. For example, wind, water forces, moving loads, dynamic forces. The possibility of maximum design load. Again, for non-routine structures, it is probably that unfavorable changes of loading will happen, whereas routine buildings are often designed on nominal loading, which is not likely to happen. Other factors are the results of failure. Public expect less risk to be taken with structures, the failure of which could bring about catastrophic consequences. More risk is taken with temporary works than permanent ones. The ambiguity of soil model, inaccuracy of strength values, water table fluctuations, mode of failure, limitation of analytical method, all provide uncertainty. The coverage of investigation, sufficient depth, layering of deposits, uniformity of ground conditions, number of tests. The more extensive the site investigation, the more confidence there will be in the choice of the soil model. The factor of safety values regarding the above points are presented in the table below for the design of shallow foundations. Now, let me give you an example how to use the table and you will read the rest. Suppose that you are planning a hydraulic structure such as dam, and you know that in this project maximum design load is likely to happen and the consequences of failure will be catastrophic. So you go to site investigation report, examine carefully, and if you decide that the report is complete, then you can select a factor of safety of 3. Or if you think that it is not complete, there are some missing point or uncertainties, then you will adopt a factor of safety of 4. That's it. Now let us continue with practical examples. The first one is, as you see in the figure, a rectangular building foundation of 2.5 meter wide and 3.5 meter long, placed at a depth of 1.7 meter below the ground surface in a thick deposit of firm saturated clay, is needed to support a dead load of 1050 kilonewton and a live load of 975 kilonewton. The water table is at 1.2 meter below the ground surface, and the related soil parameters are as follows. Now, you are required to determine the net allowable, in other words, safe bearing capacity using ASD for the most critical condition. And the local codes suggest that a factor of safety 3, theta of unity, and phi of 0.8 should be adopted. The most critical condition in this example is undrained one. That is to say, when the internal friction angle is 0 for saturated clay soil. In this case, the first step is to calculate the bearing capacity, shape, and depth factors. They are already done for you. The second step is to calculate the ultimate and allowable bearing capacity. For undrained condition, the related ultimate gross bearing capacity is as given here. After computing the ultimate gross bearing capacity, Q ultimate net, which is the ultimate net bearing capacity, can be obtained as a difference between the ultimate gross bearing capacity minus the weight of excavated soil. And then, if you divide Q ultimate by a factor of safety, you get the allowable net bearing capacity. Example 2, for the foundation given in example 1, determine the net allowable bearing capacity using allowable stress design for the long-term condition. The long-term condition is the drained one. So the parameters required in the calculation of net allowable bearing capacity are C prime and phi prime. In this context, the first step is to calculate the bearing capacity, shape, and depth factors. As you see, the bearing capacity factors, the shape factors, and depth factors are calculated for you. The second step is to calculate the ultimate and allowable bearing capacity for the drained condition. So remembering the ultimate gross bearing capacity equation as given here and putting the related data in their places, the gross bearing capacity is then calculated as given here. As explained before, the ultimate net bearing capacity is the difference between the gross ultimate bearing capacity minus the weight of excavated soil. And the allowable net bearing capacity is the ratio between the ultimate net bearing capacity and the factor of safety. These are already calculated for you. Example 3. Determine the size of a rectangular footing in example 1 using allowable stress design and load and resistance factor design for the long-term condition. The first step is to calculate the imposed load based on ASD and LRFD. These are done for you. It is very simple and you know what they are. Step 2 is to calculate R and Q. For these, we need Q ultimate gross and Q allowable gross. They are already calculated. If we Multiply these values by the cross-sectional area of rectangular footing, we get R and Q as illustrated. Now the third step, check the suitability of foundation size. For these, we need to obtain factored R, which is 5 times R. This is greater than the factored live load plus dead load. So the foundation size is acceptable. Regarding allowable stress design, the load, which is calculated here, is also greater than the total vertical load, which is dead load plus live load. So in this case, the footing size is also acceptable. But the question is, what if the foundation size is unacceptable? Well, you will try other footing sizes until you meet the requirement. That's it. Final example. The rectangular footing in example 1 is 0.5 meter thick and backfilled with soil of unit weight 19.5 kilonewton per cubic meter. If the column with vertical dead load of 1050 kilonewton and a live load of 975 kilonewton is placed 0.6 meter away from the center of the foundation on the long axis, what will be the net bearing capacity and the factor of safety against general shear failure for short-term condition? In the solution of this problem, the first step is to calculate the total vertical load, which is the summation of the weight of backfill, the weight of foundation, the dead load, and the live load, which is around 2,339.2 kilonewton. In the second step, the eccentricity and the effective size of footing should be calculated. We have only one way eccentricity, as we said, which is along the long axis. This means that the width of footing will not change, but the length of footing will be reduced due to eccentricity, and the amount of reduction is about 2 times the eccentricity. In the third step, the bearing capacity, shape, and depth factors are computed. These are already done for you. The fourth step is to calculate the net ultimate bearing capacity and factor of safety. Now, based on the related equation, the ultimate gross bearing capacity is calculated. Ultimate net bearing capacity is the difference between ultimate gross bearing capacity and the weight of excavated soil. Now, gross applied pressure is the ratio between the total vertical load acting on foundation and the reduced area of footing due to eccentricity. So the net applied pressure will be the difference between gross applied pressure and the weight of excavated soil. The factor of safety can then be estimated as a ratio between the ultimate net bearing capacity and the net applied pressure, which is about 1.52. Now then, it is quiz time. let us recap what we have learned so far. The first question: which of the following factor or factors can affect the bearing capacity of soil? Which one? No. Yes, you got it. The answer is D. All of them. The second question: a foundation design must satisfy two fundamental requirements, namely ultimate limit state and serviceability limit state. True or false? Well done. The answer is A. True. And the third question: LRFD considers uncertainties in what? Which one? No, it's not. Sorry, it is not. The answer is D. All of them. The fourth question is: which of the following is not the characteristics of general shear failure? Which one? No, it's not. It is not. The answer is D. No peak value and ultimate value not defined. The fifth question: the earth pressure coefficients are functions of the soil friction angle. False or true? Which one? Yes, the answer is B. It's true. And the sixth question: which of the following is incorrect? No, 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 no. The answer is A. Tazaki's equation is best for any situation, which is incorrect. Question 7. The bearing capacity of cohesive soils with low permeability is the most critical one immediately after construction. True or false? Yes, it is true. The answer is A. Good job. The eighth question: the allowable bearing capacity of a sand is independent of the stress history. True or false? No, it is false. The answer is B. You got it wrong. And the ninth question: if the water table lies with or more below the foundation base, then the general bearing capacity equation requires modification. True or false? Which one? Yes, you got it. The answer is A. It's false. And the final question: the selection of factor of safety is independent of the consequences of failure. True or false? Be careful. Which one? Yes. The answer is B. It's false. Well, this brings me to the end of my lecture. Thank you for your interest. Have a great weekend.